All right, so sometimes it's easier to solve these things using MATLAB, I think. Oftentimes it's a lot easier to solve these problems using MATLAB than it is to use your calculator. And I know you guys are a lot more comfortable with your calculator, and that makes sense because you've been using it for a lot longer. But I wanted to show you how I might approach a problem like this when using MATLAB. This is one that my section looked at in class. Let's take a look at it. First thing I need to do is convert this guy over into the frequency domain. All right, so I can see that my omega equals 10 radians per second. Okay, so that means that my current source is 5 angle 0. I have 5 ohms. I have, in this case, j omega times 0.4. The capacitor is minus j over omega times 0.02. And then I have, okay, capacitor on top, resistor down low. And this guy is negative j over omega times 0.1. And this guy is 5 ohms. And our goal is to figure out the phasor here of VO. Now, first thing I look at when I'm solving this problem is essentially to think, what's the easiest way to solve it? Well, I want to figure out the voltage across this resistor down here in this last leg. So one thing I could do is a current divider, right? So here's I1, I2, I3, and I4. I'm going to label it that way. Current divider is kind of a messy relationship. What I want to do is I want to figure out the voltage across this entire parallel combination of impedances. And then I'm going to use a voltage divider relationship on this last leg to figure out the voltage across here. So let's try to do that. All right, so in this case, what I'm going to do is I'm going to say I equals 5. And so I'm going to say that my total Z is equal to, since I have a bunch of things in parallel, 1 over 5 plus 1 over j omega times 0.4 plus, now it's 1 over the impedance of the capacitor. So the way that I do this is I will say that this is omega times 0.2 divided by negative j. And then here I say plus 1 over 5 minus j over omega times 0.1, like that. Okay. So notice on this middle term right here, right, I did 1 over negative j over omega times 0.2, right? And that's what led to it looking the way that it does. Okay. All right. Now, that's my total impedance. So that means that the voltage here, the voltage V across the whole thing, is equal to I times Z. Okay. Now the way that I look at this is I would then say VO is equal to V times 5 over 5 minus j over omega times 0.1. Now what did I do there in that last step? I basically said, you know what? After I got that total impedance, I could convert this whole network down into, all right, I know the voltage V across this guy. So I could use all of this. So in other words, this result right here tells me the voltage across each branch of that network. So if I look at the last branch, I have a voltage V across it. I have minus J over omega times 0.1 here. And I have V naught right there. All right? So I could just do a voltage divider relationship there at this point. Right? Since I have the same current, so maybe that's the key thing. When I have the same current through two elements, and I know the voltage across them, I can go ahead and do voltage divider at that point. Okay, that's my clue that I can do a voltage divider. So, all right, what I'm going to do now is I'm going to try to bring this into MATLAB. All right, rather than trying to do a lot of simplification, MATLAB will make this a little bit easier for me. So, all right, I open up my MATLAB and I'm going to create a new script. I'm going to call this guy example circuit problem basic. Okay, move this over here. And I'm going to define a couple of things. I'm going to say omega is equal to 10. Okay. I'm going to say I is equal to 5. Those are my currents and my omegas. All right. Now I'm going to say Z, the Z total that I've got here. Let me bring that into focus. Okay. My Z is equal to 1 over 5, and I can space this a little bit so it becomes a little bit clearer to me, plus 1 over J times omega times 0.4. So notice MATLAB recognizes J as the imaginary number. Alright, so we're good to go with that. Plus omega times 0.2 divided by minus J plus 1 over 5 minus J divided by omega times 0.1. Okay, so that's everything, and then I close the bottom parentheses. So I can do a parentheses check there. Notice one thing that MATLAB does nicely. Let me close this off. So notice when I do this, notice the blue kind of flashes over, so it shows me where it's what parentheses it's closing. So then I'm going to do this one, and it shows me that it's closing everything on the bottom. Okay, so quick check. 1 over 1/5 plus 1 over j omega 0.4 plus omega times 0.2 over negative j, 1 over 5 minus j times omega times 0.1. All right. Now one thing some of you guys may be asking, I could bring the minus 1 over j up top. Okay. So this there's 1 over minus j could become a plus j on top. I'm just leaving it the way it is. Nothing wrong with it. So that's z. Now I can say v is equal to I times z. And now I can say VO. So let's see. Let's look back at the math here. All right. So V equals I times Z, and then VO I can say is equal to V times 5 over 5 minus J times J over omega times 0.1. Boom, boom, like that. Okay? All right. And so the end of this, I probably want to get the magnitude of VO. So in MATLAB, I say abs of VO. All right. If I don't put a parenthesis or a semicolon after that, I'm going to get what the actual answer is. And then I get the angle of it. Now MATLAB's going to answer by default in radians, so I'm going to multiply that by 180 over pi to get the actual answer. So now I'm going to run that. Okay, so I run that. I go back to my MATLAB command window where it should have told me the answer. Alright, so it's told me, so here's where it ran it, example circuit problem basic, and it's telling me the answer is, if I go down, looks like what it's decided is the answer is VO has a magnitude of 2.67, I guess I'll round up, 2.678 volts. And the angle of VO is equal to negative 66.32 degrees. Okay? So in other words, if I said what is VO of t, that would be 2.678 cosine 10t minus 66.32 degrees. Right? In other words, the input voltage leads this guy by 66 degrees. So our input voltage, or the input current, sorry, the input current was where we got, right? So the input current was 5 cosine 10t. So the input current is apparently here. And then this guy is, I don't know, somewhere down here, VO, like that. Right? Negative 66 degrees. So this would be negative 66.32 degrees. Okay, so I'll attach with this that MATLAB code, all right, which is sort of a simple way to try to process these things.